Welcome. Today we're going to discuss differentiation rules. As you remember last time, we discussed derivative. We gave the definition of the derivative that you can see now using the limits. However, for generic functions, computing the derivative using the limit definition is very time consuming, very hard, right? Etc. So it's better to find out some easy ways to take the derivative. So basically in this section, that's exactly what we're going to do. We'll define certain rules of derivative that makes our life easy when it comes to find derivatives. So learning objectives are, we will learn how to take the derivative of powers, multiples, sums, and differences. Moreover, we'll discuss the derivative of exponential function. We will learn product rule and the quotient rule for derivative. And then finally, we end with second and higher order derivatives. All right, so let's get started. So derivative of powers, multiples, sums, and differences. The first one is constant function. So what is the derivative of constant function? It's 0. Let's quickly see it. Here is a brief proof. So by definition, derivative of a constant function is nothing but a limit as h goes to 0 of f of, let's write as f because my function is f, so f of x plus h minus f of x divided by h. Well, limit as h goes to 0. What is f? F is just c, it's constant. So at x plus h it's still c, and f of x is also c divided by h. So this is limit of 0 divided by h. H is not 0, it's approaching, but it's not 0. So 0 divided by h is 0. That's why this limit is 0. So the limit of a constant, a derivative of a constant is 0. The power rule for integer powers. So if n is a positive integer, then the derivative of x to the n is n times x to the n minus 1. So to prove it, we will use the following binomial formula and use the following definition of the derivative, following version, right? If you remember, the derivative of a function at x was the limit as z goes to x, f of z minus f of x divided by z minus x. I wrote it so that it sort of matches the binomial formula. Now let's take our f of x or f of z to be this power z to the n, or x to be x to the n. So then the derivative of x to the n would be, it's f prime of x. So this is by definition as z goes to x. So f of z is z to the n because the function is the power of z, minus, if you substitute z equal to x, this is x to the n divided by z minus x. Well, if you let z go to x, it goes to 0 over 0, so we cannot immediately let z go to x. We need to cancel out, and what will cancel out is, as you can see from binomial formula, z minus x at the bottom. So z to the n minus z over x, as you can see from the binomial, it's z minus x multiplied by z to the n minus 1, etc., x to the n minus 1. So z minus x is cancelled, and I'm left with z goes to x of z to the n minus 1 plus z to the n minus 2 times x plus dot 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 zx to the n minus 2 plus xn minus 1. Now, as this is a continuous function, right? This is a polynomial. It's a continuous function. So for continuous functions, the limit is nothing but assignment, right? So I can simply let z is equal to x. So then you will get x to the n minus 1. Here it's again x to the n minus 1 because this is x to the n minus 2 multiplied by x, right? So you can see that all of these terms are x to the n minus 1, etc. Well, how many of them do I have? I have n many, right? This is repeated n times. So it means I have n times x to the n minus 1 as I wanted. In fact, more is true. So this is the general power rule. So again, the derivative of x to the n is like before, n times x to the n minus 1. But now I don't require n to be just a positive integer. In fact, n can be any real number. It can be a whole number, it can be negative number, it can be positive number, it can be irrational, etc. So all I care is that this power needs to be defined. Okay, so for the proof we will need later sections. So we're not going to prove it. Instead, we'll do some examples. So let's do some of them. So let's do A. So derivative of x cubed with respect to x. Well, here n is equal to 3, so this is simply 3 times x to the 3 minus 1, so this is 3 times x squared, right? So B, we can also write in the form like 2 over 3 prime. If you don't want to use d over dx, it's also fine. So again, here n is equal to 2 over 3, so this is going to be 2 over 3 times x to the 2 over 3 minus 1, right? So this is 2 over 3 x to the minus 1 third. Right. Let's do C. X to the power square root of 2. Take the derivative. It's square root of 2. X to the square root of 2 minus 1. The next seems somewhat interesting. 1 over x to the 4. So it's not in this x to the n form, right? This is 1 over. So how do we handle this derivative? Well, first we can rewrite it as x to the minus 4 and then take derivative. And now we see that n is minus 4, so this is like minus 4 times x to the minus 4 minus 1, which gives us minus 4 times x to the minus 5, not minus 3. The E and the F is not similar, so I leave them as exercise. Our next property is regarding the constant multiple rule. So what it says is if you take the derivative of a function which is multiplied by a constant, then it is nothing but the constant times the derivative of a function. So you can take out the constant factor. So let's quickly prove it. Proof is not hard. So the derivative of c times u, so u is my function here, c is the constant, so this is by definition, as h goes to 0, c times u of x plus h minus c times u of x divided by u. And as you can see that I can take it out the c, so this becomes limit h goes to 0. This is by the property of the limit, right? So limit as h goes to 0 of u x plus h minus u of x divided by h, which we realize it as c times the u prime of x, right? So derivative, or you can rewrite it as du dx. So that's the proof. Let's give an example. Let's say that we want to take the derivative of 5 times x 7, right? Well, by the constant multiple rule, I can take out the 5, so this is nothing but the derivative, 5 times derivative of x to the 7, and we know that derivative of x to the 7 is nothing but 7 to the x to the 6, so 5 by 7 is 35 times x to the 6. Our next property is summation rule. What it says is the derivative of the sum of two functions is sum of the derivatives. Again, let's quickly prove it. So derivative of u plus v, by definition, this is limit as h goes to 0. This is u plus v, I'm regarding as one function, x plus h minus u plus v of x, everything divided by h. Now that we know that u plus v of x is ux plus uv, so we can write them separately. So this becomes limit as h goes to 0. I can write it as u x plus h minus, I can take out u of x, right, plus v x plus h, and from second term I have minus v of x. Everything divided by h, but let's divide them separately so it won't change it. And in fact, I could also write another limit term here, right? I can split the limits. I can do it if both limits exist, right? So I need to find out if both of them exist, but indeed they exist because the first one is nothing but u prime of x. The second one is v prime of x, or derivative of u and derivative of v, right? Because we are assuming that they are differentiable. Okay, so let's do an example. So we would like to find the derivative of this polynomial. Well, so let's write it. So this is y prime x cubed plus 4 over 3x squared minus 5x plus 1 prime. By the summation or difference rule, I can write this as follows, right? I can write it x cubed prime plus 4 over 3x squared prime minus 5x prime plus 1 prime, and then evaluate each derivative separately. So derivative of x cubed is nothing but 3x squared. We know that we can take out the 4 over 3, and then we need to take the derivative of x squared, which is 2 times the x, and then I can take out the 5, so it's minus 5 times the derivative of x, but derivative of x is 1. And finally, we have a constant 1, so derivative constant is 0, right? So rewriting, we have, simplifying, we have 3x squared plus 8 over 3x minus 5. Now let's briefly discuss derivative of exponential functions. The exponential function is written in the form a to the x for a real number a. We'll not give the derivative of a to the x, which will be covered later, but we will do it for the exponential function when a is equal to the Euler constant e. So here's the property. So derivative of natural exponential function, so e to the x is e to the x. So if you remember, what was e to the x? What was e? E is a constant, something like 2.7, etc. Right? It's in an irrational number. However, we need one of the defining properties of e to the x. So if I let f of x to be e to the x, then one of the defining properties, so this is, let me write it as a fact, is that the derivative of this function e to the x at 0 is equal to 1. So the slope at 0 is equal to 1. So this is one of the defining properties. If we assume that we know this, then we can compute the derivative of this function everywhere, not only 0. So let's do the proof. So derivative of e to the x. This is the, by definition again, limit as h goes to 0, e to the x plus h minus e to the x divided by h. You can see that e to the x plus a, e to the x is the common term on the top, so I can write it as e to the x times limit as h goes to 0, e to the h minus 1 divided by h. However, what is 1? 1 is nothing but e to the 0. So we realize that this the last term is nothing but the derivative of e to the x at 0, right? So this is f prime of 0. But we already know that this is, I mean, we assume that we know it equal to 1. That's why this is e to the x. So derivative of e to the x is e to the x itself. So now let's discuss product and quotient rules. So here's the product rule. It says the derivative of two functions, products of two functions u times v is u times the derivative of v plus derivative of u times the v. So I'm not going to give the proof, so proof is left as an exercise. So proof is left as an exercise for you. However, let's see why it seems non-trivial. So one one of the common mistakes is regard the derivative of uv as derivative of u times derivative of v, but this is not true. Here's an example. Let's say that you want to take the derivative of x squared, right? But I can write it as x times x. If the product rule was the derivative of the first times derivative of the second, this would be x prime times x prime. But then this would be, what is x derivative of x is 1 times 1, so this would be 1. However, from the power rule, we know that derivative of x squared is 2 times the x. So clearly, those two things are not equal, right? So this means all these things is nonsense, right? So this is nonsense. However, let's try to apply this product rule. So derivative of x squared, again, we can write it as x times x, or derivative. Now, according to this, it's the u, so x, times the derivative of the second term, which is, okay, let's write it, x prime, plus derivative of the first term, so x prime, times the x, right? What is x prime? Again, 1. So this is like x times 1 plus 1 times x, and this is indeed 2x, right? That's precisely the definition of x squared. So indeed, somehow we sort of checked the product rule for this polynomial case. Let's do one more example. Let's say that I want to take the derivative of x cubed times e to the x. So this is u times dv dx, so x cubed times the derivative of ex plus derivative of x cubed times ex. In the first occasion, we have x cubed times, we know that the derivative of e to the x is e to the x. And on the second term, derivative of x cubed is 3 times x squared, which follows from the power rule, times ex. So that's the proper derivative of x cubed times e to the x. Now, another important property is the quotient rule. So what it says is the derivative of u over v. So quotient of two functions is v times du over dx minus u times dv over dx divided by v squared. Again, I'm not going to give the proof. However, I will leave the proof as an exercise. So proof, take it as an exercise if you're interested. However, let's do examples. So let's take the derivative of t squared minus 1 divided by t cubed plus 1. y prime. So according to this rule, I need to write my denominator, so t cube plus 1 multiplied by derivative of t squared minus 1, right? Okay, let's write it. T derivative minus u, which is my numerator, so t squared minus 1 times the derivative of v. So what is the v? It's t cubed plus 1 derivative, and this is divided by the denominator squared. So our denominator is t cubed plus 1 squared, right? So now all you have to do is just take the derivatives, the relevant derivatives, and then simplify if you like. So derivative of t squared minus 1 is simply 2 times t, and derivative of minus 1 is 0, so it's simply 2t, minus t squared minus 1 times, so derivative of t cubed plus 1 is, derivative of t cubed is 3 times t squared, and the derivative of constant is 0. So that's what we have, t cubed plus 1 squared. You can simplify further if you like it. So let's do it. So from the first one, if you expand, you get 2 times t to the 4 plus 2 to the t, 2 times t, minus from the second we get 3 t to the 4 plus 3 times t squared divided by t cubed plus 1 squared. We see that 2t to the 4 minus 3t to the 4 is minus t to the 4 plus 3t squared minus plus 2 times t divided by t cubed plus 1 squared. So that's the derivative. Now let's turn to the part B. So we'd like to take the derivative of e to the minus x. Well, how do we do it? We can first rewrite it as a quotient, right? 1 over e to the x, and then take the derivative. So 1 is my function in the numerator, e to the x is my function in the denominator. So according to this rule, v, which is e to the x, times the derivative of 1 is 0, minus u, which is 1, e to the derivative of e to the x is e to the x, divided by e to the x squared is e to the 2x. So what we have is minus 1 over e to the x. Or if you like, you can write it as minus e to the minus x. Now let's discuss second and higher order derivatives. So what does it mean to take the second order derivative? It simply means to take the derivative twice, right? You take the derivative of a function and then take one more time. So the third order derivative means take the derivative 3 times. So in particular, n order derivative means you take the derivative of the function n many times, right? And for example, second order derivatives can be written as f double prime of x, or if you like, it's d square f by dx squared, and similarly the third order derivative is can be written as d cube f over dx cube, etc. So there are other notations. So let's do an example. Let's say that we want to find f prime, f double prime, and let's say that also take the third derivative for a polynomial, right? So let's take x cubed minus 3x squared plus 5. So what would be the first derivative? It's nothing but 3x squared minus 6x plus 0, right? Just applying the summation and the constant multiple and the power rule. Then what is the second derivative? Well, second derivative, as we said, this is just a derivative of the first derivative. But what is the first derivative? First derivative is 3x squared minus 6x. So I need to take the derivative of the derivative. So we see that this is nothing but 3 times 2x minus 6. So this would be 6x minus 6. And similarly, if you would like to take the third derivative, you simply take the derivative of 6x minus 6, right? Because this is the second derivative. So with this would be 6. Now you can continue. What would be the fourth derivative? Well, the fourth derivative would be 6, and from four derivative higher orders would be 0, right? Fifth order derivative, sixth order, all of them are 0. So I will stop here.